Today, we want to review where we're at with the solving equations business. Specifically, solving equations by reading the expression, then performing inverse operations in reverse order. So let's go over the things that we've discovered. We know that the inverse of an exponent is a reciprocal exponent. That's the big thing that's driving what we're doing in this solving equations business, aside from reading the expression. We want to be able to read radicals as fraction exponents. And we've also added negative exponents by noting that variables in denominators will have negative exponents. And then we opened up a can of worms. An equation with an even numerator exponent will have 2 or 0 real solutions. This raises a question. What do you mean 0 real solutions? 0 real solutions means that we'll have 2 complex solutions. Complex solutions will be using the imaginary unit I, which is the square root of -1. I is the imaginary unit such that when you square it, you end up with -1. No real number can have this property because when you square a real number, you copy the sign so that the signs have to be the same. If x is positive and it's a positive times a positive, that's positive. If x is negative, then it's a negative times a negative, and that's positive. What this really leads to, this goes even further. It's more than just 2 real solutions or 0 real solutions. If we have x to the n power equals some constant, we'll have n complex solutions. So when we look at x to the 5th equals 1, there's 1 real solution, 1, but there's 4 other complex solutions. But we need trig for those, and that's how far this rabbit hole goes. So the rabbit hole kind of goes all the way down to the fundamental theorem of algebra, or some equivalent to the fundamental theorem of algebra. So here's what we need to know for our purposes in this class. So the wild rabbit hole is that all an nth degree, x to the n, so an nth degree polynomial equation will have n complex solutions. So I'm going to cast avoidance and say if your equation comes down to x to an even power equals a negative number, for the purposes of this class at this time, we're just going to say no real solutions. And this will be super effective for now. So that's going to be our strategy for now. If you end up with an x to an even power equals some negative, you're just going to say there are no real solutions. The way I'm going to remind you of this is I'll say find the real solutions of the equations. Show your calculations, round your answer to the nearest thousandth. Then when we start looking at the non-real solutions, at least in this class, just for those of you thinking about the future, we're going to stop the n at 2. So if x squared equals a negative, then I will ask for the complex solutions because there's only going to be 2 of them. If I start bringing in x to the 4th, now we could have up to 4 complex solutions, and I think that's going too far for us, mostly because we'd need trig for it. All right, so let's look at some examples. So let's look at an example function. Let's suppose that we wanted to solve the cube root of 5x squared minus 1 is equal to 4. Took me that long to come up with a number. So we see some radicals, we see some exponents. We notice that our equation has an even numerator exponent. There's an x squared. So that means we're going to have 2 or 0 real solutions. We know that there's a radical. This is cube root, so there's going to be a 1/3 power involved. And we want to consider whether we can combine all these exponents. It all comes down to reading the equation. So let's read the equation. This equation says the x gets turned into a 4 by doing some operations on it. let's read what happens to turn an x into a 4. Starting with the x, the first thing that happens is it gets squared. Here's where we notice that we could have 2 or 0 real solutions. Next thing that happens. After we square the x, we multiply by 5. After we multiply by 5, we subtract 1. And then after we subtract 1, that's when we do the cube roots, because the radical, the horizontal bar on the radical, acts as a grouping symbol. It's not the cube root of 5 or the cube root of 5x squared. It's the cube root of this whole thing, the cube root of the difference between 5x squared and 1. So fourth, there's a cube root, or a 1/3 power, because we want to read radicals as fraction exponents. And this is how the equation turns an x into a 4. So the things that we notice, because we have an even exponent in the equation, that means we have to be on the lookout for 2 or 0 real solutions. Not 2 or 0 real solutions. We know if it comes down to x squared equals a negative number, we'll stop and we'll just say no real solutions. So now we're just going to turn the 4 back into x by doing inverse operations in reverse order. So our plan for turning a 4 back into an x. First, we're going to undo the last thing that happened. The inverse of a cube root is a 1/3 power. The inverse of a 1/3 power is a reciprocal, so a 1/3 to the 3rd raised to the reciprocal exponent. Next, the inverse of subtracting 1 is adding 1. Third, the inverse of multiplying by 5 is dividing by 5. And fourth, the inverse of a square is a square root, or a 1/2 power. So we notice that at the very end is where our 2 solutions are going to show up, or 0 solutions are going to show up. So we have to go all the way to the end to find 0 solutions, but we get to just write the 2 solutions at the very end. We don't have to perform additional operations on both solutions. So let's start with a 4 and raise that to the 3rd power. That's 64. Next, so 4 to the 3rd is 64. Then take the 64 and plus 1 to get 65. Then take the 65 and divide it by 5. You get 13. And then finally do a 13 to the 1/2 power, and that's where we get positives and negatives. So we'll take 13 to the 1/2 power. 3.606. But because we did a 1/2 power, and we're looking for all the solutions. We're not just asking the square root of 13. We're looking for all the solutions. We also get the negative 3.606. There are no more operations to perform, so those are our 2 solutions, 3.606 and negative 3.606. So it comes down to reading the expression and then performing inverse operations in reverse order. Like I've said before, the limitation to this particular method is that we can only use this style of solving when the variable only appears once in the expression. So we can just track a list of things that happen to the variable x. So our strategy going forward, if there's more than one instance of x, then we're going to have to come up with a way to write the expression so that the variable only appears once, or we're going to have some other kind of technique. Any questions? Comments? Snide remarks? All right, let's take a look at another example. Let's look at one with maybe some negatives. Negative exponents, specifically. Let's suppose that we wanted to solve this equation. Let's suppose that we wanted to take the equation, let's take 10 divided by 5x squared minus 1 to the third power. And let's suppose this is supposed to equal 8. I used the same inside that I did before. At least I did a third power instead of a cube root. So here's what we notice on this equation. We got the x squared, so there's an even exponent. So there could be 2 or 0 real solutions. Let's write down what happens to the x in this equation. First, we do a square. So that tells us there could be 2 or 0 solutions because we have an even numerator exponent. Second, we multiply by 5 just like we did before. And third, we subtract 1 just like we did before. Next, things are raised to the third power. And since it's in the denominator, I'm going to read this as to the negative third power. So I can fix a variable in the negative, a variable in the denominator can be written as with a negative exponent, which is the thing that I wanted to do first. I got distracted by using the same inside, so I forgot to do this first. So I'm going to write this negative exponent, and I want to write it all in one line. I want this as 10 times 5x squared minus 1 to the negative 3 power is equal to 8. Good thing I'm not editing my videos to get rid of these mistakes. So the first thing we want to do is, since there's a variable in the variable is showing up in the denominator, we want to read it in such a way that we could read it with a negative exponent so that we can read everything as addition, multiplication, and exponents. So that 10 is being divided by the third power of the 5x squared minus 1. So I want to move all that up to the numerator and write the equation as 10 times 5x squared minus 1 to the negative third power. Now I can just list a bunch of things that happen to the x. And then the last thing is that we multiply by 10. This is how x gets turned into 8 by a list of operations. Also notice that the x squared is not a negative exponent, even though we're in the denominator. The denominator happens because the 3 exponent, the 3 applies to the whole denominator, so I pull that whole denominator up to make a negative 3 exponent. I don't want to change the x to the squared as well, because I've already moved that whole chunk of stuff up to the numerator with a negative 3 exponent. So let's do inverse operations in reverse order and turn an 8 back into an x. So first, we'll take the 8 and we'll invert the multiplying by 10 and divide by 10. Second, we'll do the inverse of a negative third power with a reciprocal exponent, negative 1/3 power. Third, the inverse of subtracting 1 is adding 1. Fourth, the inverse of multiplying by 5 is dividing by 5. And fifth, the inverse of a square is a 1/2 power, or a square root. So now, we'll just follow through all these inverse operations. So it will take the 8 and we'll divide by 10. Grab our calculator in case things gets weird. Take the 8 divided by 10, that's 0.8. And then take 0.8 and raise it to the negative 1/3 power. There you go, 1.077. Then take the 1.077 and add 1 to get 2.077. Then take the 2.077 and divide by 5. To get 0.415. And then finally take the 0.415 and find the square root, or raise to the 1/2 power. To get 0.645, we'll call it. Since we noticed that we had an even exponent, we're going to note that there are 2 or 0 real solutions. In this case, we got a real solution because we didn't have an even power equaling a negative number. So I'll have 0.645 and negative 0.645. So there are our 2 solutions. X equals 0.645 and negative 0.645. This one was a little bit messy, especially with that bad start that I put on it by not reading things with the negative exponents. But it all worked out in the end. As usual with all these things, with all these equations, we can check our answers by running them through the operations. So if I take the 0.645 and I start off by raising that to the second power, and then multiplying by 5, and then subtracting 1, and then raising that to the negative 3 power, and then multiplying by 10, we end up back where we started. If I start with a negative 0.645, which has been rounded off, so it's going to be off a little bit, and I raise that to the, I'm going to raise the negative along with it. If I raise the negative 0.645 to the second, and then multiply by 5, and then subtract 1, and then raise to the negative 3rd power, and then multiply by 10, I get 8. I didn't get precisely 8 because I rounded off my 0.645. But if I haven't rounded it off so severely, I would have come up with 8 exactly. Any questions? One more example for today. Let's suppose that I have an equation that says negative 2 times x plus 3 squared plus 7 is equal to 0. This isn't the example that I wanted. I want to do the next one on my list of examples. Change the -2 to a 5. This is what happens when you don't leave enough space between the examples that you write down. Let's get rid of this. Let's go with 5 times x minus 3 squared plus 7 is equal to 0. I wanted one with no solutions. Same strategy as before. We're going to see what happens to turn an x into a 0. First of all, we notice that there's an even exponent, even numerator exponent in the equation, so there could be 2 or 0 real solutions. Let's write down what do we do to turn an x into a 0 in this equation. First, we subtract 3. Second, we got multiplication and exponents go before multiplication, so we'll raise to the second power. Now we've identified that there could be 2 or 0 real solutions. Third, we have multiplication and addition, and multiplication goes before addition unless there's some grouping symbol that says otherwise. So we'll multiply by 5. And fourth, we'll add 7. Our plan for solving to turn a 0 back into an x. The first thing we're going to do is subtract 7. And the second thing we're going to do is divide by 5. And the third thing we're going to do is do a square roots or a 1/2 power. And this is where we'll see that there's going to be 0 solutions. Actually, we saw it right here. -7, 0 minus 7 is negative. Divide by 5, still negative. Square roots, not real. But let's write down our plan anyway. The last thing we would do if we weren't going to get no solutions is add 3. We grab our calculator. And starting with 0, we subtract 7, coming up with -7. Then we take the -7 and divide it by 5 to get -1.4. And now we have -1.4 raised to the 1/2 power. And this is where we have no solutions, no real solutions. So that's where we can stop, and we just write no real solutions. All right, those are the examples that I wanted to look at today. I wanted to emphasize the even exponent thing. I wanted to practice a little bit more with the variable in the denominator thing. And I wanted to practice a little bit more with the radicals or fraction exponent thing. So some quizzes have started to appear in the third module for on Canvas. So make sure you start doing those quizzes. That'll do it for today. I'll see you all on tomorrow, and thanks for playing.